Thanks for joining me today. Today we are going to start talking about gases and kinetic molecular theory. But before we get into that, we need to remind ourselves about the different states of matter. So obviously, you should remember that the states of matter come in three kinds. There are three basic states of matter. We have solids, liquids, and gases. So solids. Our particles are closely packed together, they have a crystal structure, but the particles, they may be touching each other more or less, but they're still kind of vibrating in place and moving around and vibrating as they are in their crystal structure, but they are in a rigid place. So because of that rigid structure, they have a definite volume, meaning their volume is the same. If I want to change the volume of a solid, I have to break parts of it off or add parts to it. They have a definite shape. So if I have a cube, it's going to stay a cube unless I do something to destroy that cube, meaning I take parts of it off, I crush it, I break it. It's going to keep the same shape unless I do something to it. And solids are incompressible, which means if I push on it, if I apply a force to that solid, it's not going to change its volume. Its volume is going to stay the same as I push on it. It's incompressible. You cannot compress it to be something less. That's a solid. Liquids are very close to solids in that they have some of the similar things. Their particles are also close together, but they're not stuck in a rigid formation. They're able to move past each other. And because they're not stuck in that rigid structure, particles can move around, move past each other, but they're still relatively close to each other within the sample of the substance. And liquids, because of that ability to move around, they have a definite volume, so their volume doesn't change. How much space they take up doesn't change, but they have an indefinite shape. Because the particles can move around, they can then take the shape of whatever container they have. That's what we mean by indefinite, is it's not a defined shape. The shape depends on what container it is in. But liquids are also incompressible. If I apply a force to a liquid, it more or less does not change volume either. This is why hydraulics work the way that they do, is I can apply a force over here and the liquid in between transfers that force to something else. And that's the way hydraulics work, and they only work because liquids are incompressible. Then we have gases. Gases, the particles are really far apart. They're flying all over the place, and they really rarely touch each other. Gases have an indefinite volume, which means they will take up the volume of whatever you put them in. If I have a small container, it'll fit in that small container. If I take the same amount of gas and I put it in a big container, it's going to fill up the big container. It's going to fill the volume of whatever container it's in. And they have an indefinite shape, meaning they're going to take the shape of whatever container we put them in also. And gases are compressible. We can apply a force to a gas and change its volume. And so we can compress it down. That's actually what an air compressor does, is it pushes the gas into a smaller volume. So that leads us to our discussion of kinetic molecular theory. So kinetic has to do with motion, and molecular has to do with molecules. So kinetic molecular theory has to do with the motion of the molecules. And kinetic molecular theory states that gas particles are in constant motion and exhibit nearly perfect elastic collisions. And we'll talk more about what that means in a couple of minutes. So there are 5 postulates to this theory, 5 postulates to the kinetic molecular theory. The first is that the volume of individual particles is negligible compared to the volume of the gas itself. We call these point particles. And so what that means is that if I have a volume of gas that's really big, the molecules that make that up are so incredibly small compared to the volume of the gas that we can ignore the volume of the individual molecules. The individual particles of the gas. We're going to ignore their volume. They do have an actual volume, but it's so small compared to the volume of the whole sample of gas that we can ignore the individual molecules or the individual particles' volume. The second postulate is that the particles of an ideal gas do not exert any forces of attraction on each other. So when one molecule one gas particle comes close to another one, they're not attracted to each other. They just go straight past. There's no interaction between them. They don't exert any attractive or repulsive forces on each other or on their surroundings. The third postulate is that gases are in constant random motion. When you say random, that doesn't mean they like sit here and go all over the place, because they travel in straight lines until they collide with something. Random means that there's not really any pattern to it. It's just they're moving. They go in a straight line until they hit something, and then they bounce off and go in a different direction in a straight line. So they move in straight lines until they collide with something. Which brings us to the collisions. In collisions, exhibited by gas particles are completely elastic. What that means is they do not lose any kinetic energy when they cram into each other. You'll learn more about kinetic energy and elastic collisions in physics, but when we talk about collisions of particles in chemistry, we're talking about completely elastic collisions. So two particles bang into each other and bounce off, and the total kinetic energy is not changed. Nothing is lost in that collision. The fifth postulate, and the one we're going to focus on for a lot of the rest of our discussion today, is the average kinetic energy of gas molecules is directly proportional to the absolute temperature. So when we're talking about the absolute temperature, that means we have to actually know what temperature is. Well, temperature, by definition, is a measure of the amount of kinetic energy of the particles in the substance. It's the average kinetic energy of the particles in the substance. And it's calculated very complicatedly, more or less, but it's an indirect measurement that we do when we measure temperature. So we're not going to really get into that right now, but what we do need to understand is what it is. Temperature is a measure of the average kinetic energy of the particles of a substance. When we say average, that means some particles may be moving faster. Kinetic energy has to do with how fast they're moving. So a fast-moving particle is going to have more kinetic energy than a slow-moving particle. It also has to do with mass. So a large particle is going to have more kinetic energy than a small particle that's moving the same speed. So mass and velocity have to do with the kinetic energy. So if you have some particles may have a large kinetic energy because they're moving really fast, and some particles may have a lower kinetic energy because they're moving relatively slow. But if you take all of the particles in a gas together and you average that up, that gives us an average measure of the average kinetic energy, and that is what temperature is. Now, absolute zero, because the postulate said that the absolute temperature, well, absolute zero describes the situation in which average kinetic energy of particles is zero. So it's the situation where all particle motion stops, because in order to have zero kinetic energy, they can't be moving. So all molecular motion has stopped. That is absolute zero. It is a zero temperature, meaning no kinetic energy of the particles. So in order for an average to be zero, that has to be completely zero. Now, we have three different temperature scales that are used throughout the world. And we're going to talk about those three temperature scales and which ones we're going to use. And there's one that we're going to use more than any of the rest moving forward. All right, so we have the Fahrenheit scale, developed by Daniel Fahrenheit in the 1700s. And the original definition was he based this off of the temperature of a solution of water, ice, and ammonium chloride. I don't know the exact concentrations and proportions of this solution, but he set that temperature as zero. It's just arbitrarily said that the temperature of this particular solution, that is 0 degrees. And then he said, we're going to say, well, 96 degrees is human body temperature. And so that was the best estimate given the measuring equipment that they had at the time. We now know that the actual average human body temperature is 98.6, so it's a couple degrees different based off of our current definitions of the Fahrenheit scale and our current measuring techniques. But this is what he based his temperature scale off of. And so between the temperature of that solution and human body temperature, there were 96 degrees or 96 gradations, 96 markings on your thermometer. Now, that was the original definition. Currently, we use water to define most temperature scales. And so the Fahrenheit scale is currently defined as 32 degrees being the freezing point of water, the temperature at which water turns from a liquid to a solid, and the boiling point, the temperature at which water goes from a liquid to a gas, of 212 degrees. Now, both of these are taken at sea level and 1 atmosphere of pressure. So the 32 degrees Fahrenheit is the freezing point of water, 212 degrees Fahrenheit is the boiling point of water, and there is a 180-degree difference between the freezing point of water and the boiling point of water. That comes into play in a little bit. So it's exactly 180 degrees between the freezing point and the boiling point. So this is the Fahrenheit scale. And consequently enough, the United States is the only industrialized country in the world that still uses the Fahrenheit scale exclusively. A few other countries will use the Fahrenheit scale occasionally, but they all have the official temperature scale that they use is our next one on our list, which is the Celsius scale. This is the metric version. It's also called centigrade and was originally called the centigrade because centi meaning 100 and grade meaning gradus, or from the Latin gradus, which means markings or gradations, levels. So the Celsius scale was also called the centigrade scale, or 100 levels. And its original definition was 0 degrees Celsius was the freezing point of water, and 100 degrees Celsius was the boiling point of water. Now, I say the original definition. That's actually not true. The very, very first version of this was actually flipped, where they had 100 degrees Celsius as the freezing point and 0 degrees Celsius as the boiling point, which meant all temperatures that we normally use were negative temperatures, because if you're doing something that's less than the boiling point of water, like the normal room temperature is between the boiling point of water and the freezing point of water, and so on the very, very original Celsius scale, room temperature would have been negative. That's problematic. People don't like dealing with negative numbers, so they flipped it. But still, it was based off of 0 degrees as the freezing point, 100 degrees as the boiling point, hence the name centigrade, 100 levels between freezing and boiling. Now, currently, because a few years ago when the scientific community redefined all of our SI standard base units in terms of scientific constants, the Celsius temperature scale was also redefined. It's currently based off of and defined by absolute zero. Negative 273.15 degrees Celsius is absolute zero. And that is also defined off of the triple point of pure water, and we'll talk about triple point later. Now, then on the Celsius scale, though, there is a 100-degree difference between the freezing point and the boiling point of water. So we've redefined how we measure the Celsius scale, but what it actually is hasn't really changed. So the size of a Celsius degree, those levels, those gradations between temperatures, is still 100 grades, 100 levels between freezing and boiling of water. So you'll notice that freezing and boiling of water has a big deal to do with this. It's because water is so incredibly abundant on Earth, and it's got a very wide range between freezing and boiling point. We'll get into that more in another unit. The third temperature scale came about. It's called the Kelvin Scale, developed by Lord Kelvin. It's also called the absolute temperature scale because it's based off of this absolute zero concept. Now, the whole point of the Kelvin scale is that absolute zero is 0 Kelvin, and if you cannot go below absolute zero, it's the absolute zero. Cannot go less than that, because again, temperature is the measure of all molecular motion. Well, if at absolute zero molecular motion stops, then you can't have negative molecular motion, and so you can't have a negative temperature. And that's what makes the Kelvin scale very, very useful, is it can't be negative, all right? But what they did when they set it up, they just simply basically moved where zero was on the Celsius scale and said that the Kelvin zero is going to be the 0 point of our graph. but then it's going to be a same size as the Celsius. So 1 Kelvin is the same as 1 degree Celsius, or a change of 1 Kelvin is the same as a change of 1 degree Celsius. It's the same size degree. And I want you to notice the way I'm talking about this. We don't say degrees Kelvin. A Kelvin is a unit, just like a meter is a unit. All right, so we have 1 Kelvin and 1 degree Celsius. So degrees are levels or grades of something. Kelvin is its actual unit. So 1 Kelvin, 2 Kelvins, 3 Kelvins. So we don't say degrees Kelvin. It's just a semantics thing. Now, currently, the Kelvin scale is defined by something called Boltzmann's constant. That's one of those scientific constants that helped redefine the SI units. Now, Kelvin is the SI base unit temperature scale. So if you're using the official SI system, you're going to be using Kelvin. It is the one that is going to be used by scientists most. Now, we do use Celsius a lot because a lot of our measuring tools and a lot of countries use Celsius as their official temperature scale. But in the science lab, we most often are going to use the absolute temperature scale. And it's really awesome because you never end up with a negative number on the Kelvin scale. But on the Kelvin scale, there is still a 100-degree difference between the freezing and the boiling point of water. It's just the freezing point of water is not 0. So absolute 0 that the Kelvin scale is based off of is this theoretical temperature that is extrapolated from a linear graph of temperature versus volume. This is how we ended up and got the values for the Kelvin scale. So if you take a graph of your volume versus your temperature measured in Celsius, the volume of a gas and its Celsius temperature, as you decrease the temperature, the volume is going to decrease. All right? And as you decrease the volume, when you get to 0 Celsius, you don't have 0 volume. Well, theoretically, if you continue that process, then when you get to 0 volume, you will have 0 temperature because you'll have 0 particles. It's a little bit more confusing, so it's a theoretical thing. But you take that graph of volume and temperature that you see here, and if you extrapolate it backwards, that's what the dotted line is, that extrapolation, or we're going to project the line backwards to where it would cross the x-axis on the temperature scale. Well, that is a value of negative 273 degrees Celsius. And so that is the value of absolute 0. Absolute 0, or 0 kelvins, is equal to negative 273.15 degrees Celsius. So when we're going to convert our temperature scales, since we don't always use the correct temperature scales when we measure things, sometimes we'll measure things in Fahrenheit, but when we need to do calculations, we need them to be in a certain temperature scale like Kelvin or in Celsius. So to convert temperature scales, we've got these different conversion factors and equations. There's actually an equation that converts between Fahrenheit and Celsius. So to convert from Fahrenheit to Celsius, you're going to use this equation. Your Celsius temperature is going to be equal to 5/9 times your Fahrenheit temperature minus 32. So if you think about the order of operations here, you're going to have to do what's in the parentheses first. So I'm going to have to take my Fahrenheit temperature, subtract 32, and then I'm going to multiply that by that fraction of 5/9. So multiply it by 5 and divide by 9. And that's how you get your Celsius temperature from Fahrenheit. Your Fahrenheit temperature, if you're going to go from Celsius to Fahrenheit, you're going to do kind of the opposite equation. Your Fahrenheit temperature is going to be 9/5 times your Celsius temperature, and then you add 32. So again, you have to make sure you follow the order of operations. I'm going to do some examples of these in a few minutes. Then your Celsius to Kelvin. If I want to convert from Celsius to Kelvin, which is what we're going to do a lot because oftentimes we measure our temperatures in Celsius, but we need to use them in kelvins. So to go from Celsius to Kelvin is pretty simple. You simply take your Celsius temperature and add 273. Now, I realize that the official definition would be 273.15, but because of the significant figures that we most often use when we are measuring our temperature scales, it's going to be truncated off anyway. So we're going to say, just to make life easier, 273 is perfectly fine for our purposes. You should know, though, that it is actually 273.15, but you don't actually have to add the 0.15 when you're doing this because it's going to go away with significant figures most of the time anyway. Now, if I want to go from Kelvin to Celsius, because sometimes I'm going to ask you to tell me your answer in Celsius, but you're going to calculate it using Kelvin, and then you have to tell me the answer in Celsius. Well, to find Celsius, you simply take your Kelvin temperature and subtract 273. So these are very, very easy conversions. From Celsius to Kelvin, you add 273. From Kelvin to Celsius, you subtract 273. Now, if I wanted to go from Fahrenheit to Kelvin, then I'm going to have to go from Fahrenheit to Celsius first, and then Celsius to Kelvin. Or if I want to go from Kelvin to Fahrenheit, I go from Kelvin to Celsius first, and then from Celsius to Fahrenheit. Because there's not really a relationship between Kelvin and Fahrenheit that's an easy calculation. So it's just best to just go to Celsius first and then go to Fahrenheit, or go from Fahrenheit to Celsius and then go to Kelvin if you need to make that kind of a conversion. So now let's get into doing some examples of these temperature conversions. What is the average human body temperature in kelvins? So average human body temperature is 98.6 degrees Fahrenheit. So I'm going to have to convert this 98.6 degrees Fahrenheit into kelvins. So first I'm going to have to convert it to degrees Celsius. And so my degrees Celsius is going to equal 5/9 times my Fahrenheit temperature minus 32. Okay, so I'm going to take 98.6 minus 32 times 5/9 is equal to my Celsius temperature. So in our calculator, we do 98.6 minus 32, and that's 66.6, and then that's times the 5/9. So I'm going to multiply that by 5 and divide by 9, and that gives me 37. So that's 37 degrees is my Celsius temperature. So the question, though, wants it in kelvins. So then to go from Celsius to Kelvin, my Kelvin temperature is going to be my Celsius temperature plus 273. So I simply take my 37 and I add 273 and I get 310 kelvins. Okay? Now, since I started out the whole thing, these are just conversions, and since we're doing conversions, we have to look at significant figures. Everything in these equations are constant. So when we're looking at conversions, whatever I started with here is going to be my number of significant figures. So this is 310 kelvins. This is actually only 2 significant figures. So in order to get 3, I'm going to need to put a decimal there to make that 0 significant, or I could do 3.10 times 10 to the 2 kelvins. I can either put a decimal here, which is probably the easier way to do it, or put it in scientific notation. But that is my answer for the average human body temperature in kelvins. All right, what is room temperature in kelvins? Well, room temperature is generally accepted as 20 degrees Celsius. So I want to take 20 degrees Celsius and figure out how many kelvins that is. Again, this is a very, very simple one because to go from Celsius to Kelvin, our Kelvin temperature is simply our Celsius temperature plus 273. So I take 20 plus 273, and that gives me 293. And that's 293 kelvins. Now, I just said 20, so we can make it 20.0 for significant figures purposes. If it was 20 exactly, then it would just be 300 Kelvin, but that's not really important at the moment. So we're just going to add it and get our 273. Now some people would say that room temperature is 25 degrees Celsius. So we'll say that's 25.0 degrees Celsius. In that case, if we added 25 to 273, it would be 298 kelvins. I've heard 20 degrees Celsius used. I've heard 25 degrees Celsius used as room temperature. So if I were to actually give you a problem like this on an assignment, I would specify what the actual temperature is. But the point here is that converting from Celsius to Kelvin is really simple. You simply add 273 to your Celsius temperature. All right, so now this example is actually an exercise in algebra because it's asking what temperature is your Fahrenheit and your Celsius the same, okay? And there is a temperature where Fahrenheit and Celsius scales meet because they're both a linear graph. And actually, if you look at it, they're both linear graphs. They just have different slopes. If you look at the equations, you've got the 5/9 and the 9/5 and all that stuff. So you'll have a Fahrenheit graph and a Celsius graph, and that's actually not a good drawing of it. So let me do a better one. If you have a Fahrenheit graph and a Celsius graph, they are going to meet at some point. They've got different 0 points where your temperature is 0, your volume is different. But anyway, I'm not going to get too much into the graph of that, but there is a point where they will cross and you'll get the same answer for both. So to do that, we're going to take one of the two equations, and let's just say we're going to take the Fahrenheit equals 9/5 C plus 32. And I'm going to take this equation right here. Now, if Fahrenheit and Celsius are the same, then I'm going to just make these the same variable. So I'm just going to call that x. So x equals 9/5, and this is also x. So they're both the same temperature plus 32. Well, now I can solve for x. So if I have 9/5 x over here and x over here, I need to subtract this. So that's going to give me x minus 9/5 x equals 32. Well, this could be written as 5/5. So 5/5x, that makes the fraction a whole lot easier to work with. So 5 minus 9 is, and I'm running out of room, so 5 minus 9 is going to be a negative 4/5. X equals 32. So now to get x by itself, I'm going to multiply both sides by 5 to give me negative 4x equals, and then we do 32 times 5, which is 160. And then I'm going to divide both sides by negative 4 to get x equals a negative 40. That's 160 divided by 4 is negative 40. So at negative 40 degrees, you've got negative 40 degrees Fahrenheit is equal to negative 40 degrees Celsius. They're the same temperature at that point. So that's basically just an exercise in algebra, not really unit conversion. I just thought it was fun, and that's why I included it in there.